when you start at 27, when you start to solve the equation here, you'll recognize that you have sine and cosecant. Sine and cosecant are reciprocal properties of one another. So what you're going to try and do is set it up as 2 sine x plus 1 over sine x equals 0. Now, in order to add fractions, what do you have to have? Common denominator. Very good. So the common denominator here is going to be sine. So you have a sine on the bottom, sine of x here, and then you have 2 sine squared plus 1 equals 0. Now, what's nice when you're dealing with the fractional part here, I can get rid of that sine of x on the bottom because it equals something. If I just multiply both sides by sine of x, that sign goes away. Everybody okay with that?
Yeah.
So I multiply both sides by sine of x, I get that. Now I'm at a 2-step problem. Subtract 1, divide by 2. And what's the reason why it's no solution?
Because there's like root 2.
Can't square root the negative number.
Sure, that was.
That's why. That's why you get no solution. Okay. Yes, sir.
What if you like, go, please go up a little bit. Yeah, what if you set it up as 1 over cosecant without that?
You get the same basic idea where you still wind up having to take the square root of a negative, and it's not going to work. If you set it up with the cosecant, you have 2 over cosecant of x. You still have to get the common denominator. So you wind up with 2 plus cosecant squared of x equals 0. And then cosecant squared of x equals negative 2. Will you ever get a negative 2 for a cosecant? Same idea. Okay. Does that make sense? I haven't done the example of how to do it yet.
Oh, so you, okay.
You haven't seen how to do that problem. But it's really easy.
It's really easy.
Okay.
Just,
What else did you want to look at? 21? Sure.
21.
Cosine cubed equals cosine of x. Now, in this case, you can't divide both sides by cosine because you would eliminate a possible solution. So what you do is you subtract it. GCF. Now you have 2 separate terms that are set equal to 0. So you set them up for 2 separate terms equal to 0. So what angle has a cosine of 0? 1. That's 0. Pi over 2. This one is what angle has a cosine of plus or minus 1. That's at 0 and pi. And then did it ask for general solution in this one? Oh, I forgot this one was at 3 pi. I forgot about that one. It was in the interval. So then you just list them out, and that's all. All you had to do was list out. I forgot about the 3 pi over 2. Cosine, where's cosine equals 0? I just put pi over 2, and I forgot to write down 3 pi over 2 also, because it's also 0 at 270. So you get the 4 answers on this one.
You called me and stop.
What else you got? Anything? Should we do those other examples that we haven't done yet then? All right, let's look at the other examples. This will help you with the other ones that are on there. I think I've got 3 more to go through, and then I think that's the rest of them in this unit. Fontana and I were talking about the last 2 sections that are in this, like 5.4 and 5.5. With the half day on Thursday, we might not be able to get through as much of 5.4 as I had hoped. We might actually, because I think in the notes it says we're probably going to take one day only for 5-4. We might actually do that between tomorrow as well as Thursday with a half day, and not start 5-5 until Friday. And I think on here it said our test might be around Wednesday, so it might be closer to Thursday than Wednesday, just so we have a little bit of time. Because of all the stuff that we've done, most of this section has been the same as. What's shaking?
Another one. Mostly it's the same stuff.
I know, it's trig equations, they just don't go away. It's a bad penny.
I'm not gonna be here Friday.
We'll miss you.
I won't.
So let's look at the other examples that I had for you. One of the ways to solve an equation is to square it into a quadratic. So we're going to find all the solutions on the interval of cosine x plus 1 equals sine of x. One of the ways to solve this is to square both sides. Yeah, because then you can start to get your Pythagorean identities that you can use. So if you wind up squaring both sides, cosine plus 1 times cosine plus 1, when you FOIL that out, you're going to get cosine squared, oops, got the x, plus 2 cosine x plus 1. And then on the other side, it's going to equal sine squared. Are we okay with that? Now, notice I have cosine squared, 2 cosine squared, and a 1. And the other side I have sine squared. Do you think I'm going to convert things into cosines or sines?
I mean cosine.
Cosines, right. I'm going to convert things into cosines because I have a squared cosine and a normal cosine. So I'm going to put everything in terms of cosine. Sine squared is what in terms of cosine?
Cosine squared minus
1 minus cosine squared, good. So I get this. Cosine squared x plus 2 cosine x plus 1 is 1 minus cosine squared. So far, so good? Set one side equal to 0. Subtract 1, add a cosine squared. Cosine squared plus cosine squared is? And what do they have in common? Cosine. So. And now I'm back at 2 terms, both set equal to 0. So I set both terms equal to 0. So where do you get cosine that's equal to 0?
Pi over 2.
And where's cosine equal to negative 1? Now, the only thing that we have yet to worry about, that we haven't really done a lot of, is when we have things that are in the quadratic style, when you have squared stuff, you need to make sure to check your answers. Okay? So what happens is we have to be able to check and see, well, do your sine values, your cosine values, and all that stuff, do they check themselves through? When we look at the original problem, if you go back to the original problem, we had what was it, cosine of x plus 1 equals sine of x. So we have to check. What is the cosine of pi over 2 plus 1? Well, what was the cosine at pi over 2? What's 0 plus 1?
1.
What's sine of pi over 2?
1.
Does that work?
Yeah.
Yes. So pi over 2 is good. 3 pi over 2. Cosine of 3 pi over 2 is down at 0, negative 1, so it's 0 again. So what's 0 plus 1? But what was the sine at 3 pi over 2? It was one of those. Does 1 equal negative 1?
No.
So what you need to start checking here is when you have quadratic style, where you get extra answers, you gotta go back and double check it. Check for the extraneous solution. That's an extraneous solution, the 3 pi over 2. Okay? But then you check it again at pi. What was the cosine at pi? Negative 1 and 1 is?
0.
And then the sine at pi was? So that one works. It's not going to be ones that are going to be very difficult to check. As you can see, these run quadraticals are really fast to go through. Really fast to go through. So those are your solutions on how many. Now finally the example that helps you solve number 3, multiple angle. A multiple angle problem. Multiple angles are the ones where you see a variable mixed in with, after you see cosine, cosine 3x, cosine 6x, cosine 1/2 x, something along those lines. So what we wind up doing is we're going to solve the equation the exact same way as you would if it was a regular value. It was just x. Okay? So what I'm going to do here is just rewrite this so you can see what we're going to, how this sets itself out. We solve it just like we would here to get our general solution. Add 1, divide by 2. So what angle has a cosine of 1/2? Well, pi over 3. Okay. Pi over 3, and what other quadrant is cosine positive?
7 or 5.
There's 7
Oh, I'm sorry, I was thinking, yes. I'm sorry, man. I was thinking sine. I just had to get on with signs.
Wait, am I right?
Yeah.
Okay.
Now this is setting you up for a general solution. So on the unit circle, if we're looking at this in terms of general solution, pi over 3, 5 pi over 3, what do I do to both of those to get around to them again? Very good. So we know that x is going to equal pi over 3 plus 2 pi n, or x is going to equal 5 pi over 3 plus 2 pi n. Wait, there's more. What does x equal? 3t. So instead of this, I have it 3t equals this. So what do I do with the 3 then? Or multiply everything by 1/3. I multiply both sides by 1/3 then. So this becomes, distribute the third to both parts, you get pi over 9 plus 2 pi over 3 n.
That's your final. I don't like that.
That's it. And the same thing on the bottom here, on the next one. You just multiply everything by a third, and you're going to get 5 pi over 9 plus 2 pi over 3 n. That's the only extra step, is when you have this multiple angle, at the very end, after you've solved it for the general solution, you just move that value by multiplying by a reciprocal or whatever you have to do. Right? That's it. That's all you do. Okay, so you see how I said it's looks really weird, but in essence, it's the same problem with one little step thrown in at the very end. Isn't that what all math is? No, it's just an extra step. Just one more step. Okay, that's all that works out to be. Let's do another one with that. Oh, I already had this one. So this one I have 3 tangent of x over 2 plus 3 equals 0. So instead of letting x equal x over 2, I'll say let theta. We'll solve for theta. And we'll use like a theta substitution or a u substitution if you want. Or just solve it like you would normally, and then at the very end just move the 1/2. Doesn't matter. It all works the same. So if I write this out, it's 3 tangent of theta plus 3. Subtract 3, divide by 3. Are we okay with that? Where is tangent negative? Second and fourth, very good. At the 45-degree reference angle, so it'll be at
3 pi over 4 and 5.
Are those equidistant from one another when you're on tangent? They are. Those two guys are pi away from each other. Or 7 pi over 4.
Oh yeah, 7,000.
That's okay. 3 pi over 4, 7 pi over 4 is 1 pi revolution between each one of them, each and every time. So as far as a general solution would go, I would just write it as 3 pi over 4 plus pi n. Be okay with that? But wait, what did theta stand for?
Theta stood for 1.
Theta is x over 2. So I multiply everything by 2. And you get x equals 3 pi over 2 plus 2 pi n. Okay. So as you see, it's set up the exact same way as it normally would be to find your regular revolution, and then you just move whatever the coefficient was that was with the x value.
So they gave us like an A and a B. One of those, are those the answers then? Like, because I'm doing inverse related on
What?
Yeah. What's that? It's 3. Yeah, 3 times 2 is 6. 6 over 4 is 6. That's all. I was just that's all. And then the last one is an inverse. Sometimes you have to use a calculator to get some decimal value. Sometimes you have to, and it'll usually happen when you have a tangent. Sometimes you'll see the cosine or a sine when the values are between 0 and between -1 and +1. Remember, you can never get a cosine or a sine value that's greater than 1. If that's the case, that means there's no solution. But you could get something where, sine of x of 0.3, or I don't know, something along those lines, where you'd have to find the inverse, the arc cosine, arc sine, things like that. So if you set this one through, you have secant squared x minus 2 tangent x equals 4. This is forcing you to use what Pythagorean identity. the tangent squared one with the secant. Now, if you look at your notes, we know that 1 plus tangent squared is secant squared. That was one of the Pythagorean identities. So right off the bat, you're going to be substituting in a Pythagorean identity to help solve the problem. So we get 1 plus tangent squared minus 2 tangent x minus 4 is 0. Now what do I do? The 1 by a 4. Good, combine like terms. What's negative 4 and 1? Good. Tangent squared x minus 2 tangent x minus 3 is 0. What times what's negative 3?
Oh.
You add together to get negative 2. Because now you're at a problem where it's x squared, x, and a constant. Good. So you wind up with tangent of x minus 3 and tangent x plus 1 is 0. You okay with that? Via factoring? One of those you can get an answer relatively easy. What angle has a tangent of negative 1? So that'll be at second quadrant and fourth quadrant. So these are at 3 pi over 4, 7 pi over 4. Was this on the interval? I forget. This one's the interval. No, this was general again, so we'll rewrite that here in a second. What's wrong, Colt?
Wouldn't there be first and third quadrant?
I'm setting this equal to 0. So I get negative 1.
Okay. Yeah.
And then the other one, you have what angle gives you a tangent value of 3. Can you have a tangent value greater than 1? Yes. Remember, tangent didn't have any, it was dancing. It was doing this. It was always increasing or always decreasing. So tangent could equal 3. It's just that's where you'd use your calculator. You find some decimal value. That's what the sum is. Sometimes they do that. It actually gives you in instructions, it'll say use inverse. That means you know you're allowed to have a low decimal value. I believe that's all of these now. That should be everything. I was going through the homework questions and I don't think, whatever decimal it is. And these would be radians because you're mixed in with everything else. So you can just leave it as, I mean, I think you just leave it as the arc. It might write as arctan instead of tan inverse. I'm trying to remember how they did here. And then as you go through your, the revolution, every time it take you, what, pi to get back to another negative 3? That's all I said. Go ahead and continue working through the rest of 5.3. Can I see the homework? Mine's back there, so far away.
So far.
Seven. Approximate, that's just using your calculator. 55. Quadratic formula. If you're going to use the quadratic formula, yeah. If you look at number 55, and it's asking you to solve via the quadratic formula, 12 sine squared minus 13 sine plus 3. Okay. there should be.
Is this a certain number?
This is, what did you say this was? 55.
Is it a number?
Yeah, this is when you have. This one says use the quadratic formula to solve themselves through. So when you're looking at it, you're still plucking out the coefficients like you would normally. So you sing the song. X equals negative b plus or minus squared.
Oh, yeah.
B squared minus 4ac up over 2a.
Or you can sing my callback for the song.
Or you just summarize
Yeah,
Good
I
times.
made a quadratic.
Just say I love it.
I made a quadratic formula song to it.
Now remember, it's just not x, it's sine of x is going to equal this. The sine of x is going to equal that. Right. So you solve through the quadratic formula. What's opposite of negative 13? What's 13 squared?
169.
Oh, I'm just going to 70.
What's 4 times 3?
12.
What's 12 times 12? What's 169 minus 144?
What? Was it wrong? Gosh darn it. Close enough.
Oh, what was 8? What's 2 times 12?
24.
What's the square root of 5? 25?
Five.
So you have two possible solutions here. 18 over 24 or 8 over 24.
Either way.
And then it's just a matter of using your calculator to bounce them through. Okay?
You just put that in there and then just X equals that's it.
Yep, and then remember, you'll have two values that give you this because sine is positive in 2 spots. Two values give you the other one because sine is positive in 2 spots. So you're going to find that reference angle and go off of that.
Thank you.
Sounds good.
That is. Think of this, remember, sine's positive. So what you do the first time the calculator is going to find you some reference angle in here, which means the other, you just got to come back up off of the other one. If you're doing it in radian, if you're doing it with the calculator in radian, let me show you.
Do you do the inverse sign or just regular sign?
Inverse sign. I'll show you. If you do it in radians, slow. .85. Okay. So that's coming up this way. To be back over there, what would you do? Well, 0.85, remember this goes from 0 to pi. This is pi over 2 in radian. Pi is what decimal?
Wait, oh. I thought radian. Okay, got it.
Half of that would be at 1, let's see, divide that by 2, you get 1.57-ish. Okay? Are we okay with that? It's easy to show you this via the decimals because of the way that the calculator is doing it. If it's coming up 0.85 radian, that means it's got to be up 0.85 from here. So all you have to do to figure out the other angle is take pi minus 0.85. That's it.
Oh, and then so it's like 0.85 next time.
Yeah.
Okay.
It's the same because it's asking for it in terms of radian because I think the instruction set was in the interval of 0 to 2 pi. So you're just going to keep it in radian, but when you come up off of 180, you're coming up off of pi. So whatever radian value is, you just subtract it from pi.
And then you do the same thing the next
Yeah, exactly. Does that make a little bit more sense? I don't think we've ever really had to use the calculator before in terms of rating. So that's what that stuff looks like. Yeah. Tomorrow we'll start talking about, do you guys still have that laminated sheet we gave you guys a long time ago? It's really kind of the first time that you really need to look at that tomorrow. Because we're going to talk about sums and differences of angles in 5-4. It's not horribly difficult to do, but it's really weird if you're not careful. Okay? Yes, sir. Yes, sir. Yeah, because I believe in the question itself it says the following on the interval 0 to 2 pi. So that means when you see a pi, think radian. Huzzah!
That was fun. Yeah, not this kind.
I like elementary math.
I like 1 is bigger.
Yeah, you know, like